Hello everyone, welcome to my YouTube channel. Today I'm going to be talking about set theory. So if you haven't liked and subscribed, ensure you do so and turn on the notification bell to get notified whenever I drop more educating videos like this. That being said, let us get into the activities of today. Now, a set is a collection of well-defined objects, things or units. The objects in a set are called elements. Types of sets. Number one, we have finite set. This is when the number of elements in a set are countable. E.g., we have A is equals to odd numbers between 0 and 12. So by this now we can say countable sets. What do I mean? Finite set is when the numbers are countable, that is, it has a limited range. That's why I gave an example between 0 and 12. So the odd numbers we can say are 1, 3, 5, 7, 9, and 11. Number two, we have infinite sets, which from the name we can say is the opposite of finite sets. This is when the numbers of elements in a set are uncountable. E.g., A is equals to numbers, or we can just say 1, 2, 3, dot, 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 to infinity. So now this has no ending. That's why we have the dot. So number three, we have cardinality. Now, this is denoted by n. Okay, let's put. Okay. Now, this states the number of elements in a set, in a given finite set. E.g., A is equals to, let's use random numbers like 1, 5, 14, 27, 61. So, therefore, n in bracket A is equals to how many? 1, 2, 3, 4, 5. Like I said, it states the number of elements. These are the elements in set A, telling us that the number of elements in set A is 5. Number 4, we have empty slash null set. Now, this is a set with no elements. It is denoted as, let's say, A is equals to this. That's nothing within. Number 5, we have universal sets. So this is the collection of all conceivable objects under consideration, and it is denoted by U. No, just like cardinality is denoted by N, universal is denoted by U. So, e.g., U equals to, we can say, all English alphabets. That is A, B, C, D down to Z. Number 6. So, number 6, we have subsets. Now, if, for example, we have two sets, set A and set B, and all the elements of set A are contained in set B, then set A is a subset of set B. What do I mean? Let's say example A is equals to 1, 2, 3. Then B is equals to 1, 2, 3, 4, 5. So we can say set A is a subset of set B, and it is denoted by this, just like a C, or you can see it as a less down. So if we should write this, we'll say A subset B, or B then the opposite of A, whereby this now equals superset, telling us that B is greater than A. Just so we can see this as a less than and this as a greater than. So let's still under subsets. What if there are situations where A and B are equal? For example, e.g. A equals to 1, 2, 3. Then B equals to 3, 2, 1. So now, irrespective of how they are arranged, but since they are both 1, 2, 3, and this one from the back it can be seen as 1, 2, 3, you can just say A equals B. So in this case now, there's no subset, there's no superset, they are both equal. Number 7, we have union. Now, union, this consists of all elements belonging to two or more sets joined together. So let's say we have A equals to 1, 2, 3, then B equals to 2, 4, 6. Then we can say it's denoted by A union B, which will give us 1, 2 is here, 2 is here, 2, 3, 4, and 6. So if we were to put this in a diagram, it will look like this. This is A, this is B. So A has, what is common between them? 2, which will be here. Then A has 1, 3. Then B has 4, 6. So from here now we can say A has 1, 2, 3, which is this one, this 2, and this 3. Then B has this 2, 4, and 6. Number 8, we have intersection. So this intersection, it talks of the particular elements found in a set, which can also be seen in another set. What do I mean? Let's say we have A is equals to even numbers, or let's say 1, 2, 3, 4, 5, 6. Then B, we have odd numbers like 1, 3, 5, 7, 9. So we can say it is denoted by A small n B. Now the difference between this and this one is a small u joining all together. Now this one is a small n picking the difference. So we can say now 1 is here, 1 is here, we have 1. 2 is here, 2 is not here. 3 is here, 3 is here, we have 3. 4 is here, 4 is not here. 5 is here, 5 is here, we have 5. 6 is here, 6 is not here, and that's all. So this is our intersection. Then if we should put this in a diagram, we have something like this. A, B. Now, this intersection is just like the middle. It deals with the middle. Just as from this union, we saw what was common amongst them is the two, which is in the middle. That is it, exactly. Intersection is talking about what is common between each set. So we have 1, 3, 5, which will be 1, 3, and 5. Then the rest, which we have 2, 4, and 6, will come here. 2, 4, 6. Then we have 1, 3, 5. Then the rest will come as 7 and 9. The section is basically talking about the common variables or the common elements in each set. Number 9, we have complements. Now, complements of set A are the remaining elements found in the universal set but not in set A. If you recall from what we've been doing, it says set A is a subset of the universal set. So, complement is denoted by A raised to power, you can see like 1, or A raised to power C. Now, this is an example. Universal set, we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then set A can be 2, 4, 6, 8, 10, which are basically even numbers. Nice. They're trying to tell us that A raised to power I now is elements that are not found in set A but are in the universal set, which are odd numbers as 1, 3, 5, 7, and 9. So, putting this in a diagram, we have this. Since it's just set A, B1, B second. Then what are the elements of set A? 2, 4, 6, 8, 10. So the complements which are not in set A but are found in universal can be 1, 3, 5, 7, and 9. So that will be all for now. For our next video, we're going to be treating questions on set theory. Thank you for watching. See you later. Bye.